Yeah, in this lecture we will continue with resource scheduling. We will look at resource allocation. We had already covered this last lecture. We will look at how resources are allocated and the over allocation problem. So we will review this, then we will go into the different ways of using float for resolving over allocation. We will try to use a spreadsheet so that the calculations will be done quickly for us to see how we can really resolve the over allocation problem, the different ways to do it, and finally we will take a look at multi-resource over allocation and see what strategies one can use for this. Now let us review the problem we took last time. If you recall, we had a problem with trucks as a resource, and this was the problem statement. We said we should find the network parameters, plot the resource histogram, and then we limited saying only 10 trucks are available. Okay, so if you look back in your notes, you will find that we solved this problem last time. This was the network. Okay, we had a 15-day project duration. We had the critical path going through A, B, C, F, G and I, and when we actually took the early start schedule and we put the resources required for each day, we found that we said there was only 10 trucks available, but we found on a few days we needed more than 10 based on early start. So if we actually go back to the problem statement, we had talked about the number of trucks being required in this column of the problem statement. So again, just to refresh and review, so if A needed 2 trucks, we said it is actually 2 trucks for each day of A, B requiring 1 was 1 truck for each day of B, and this was the early start schedule which we got. So what you did was actually add up the requirement for each day for various activities. So when you came in here, you had 14 trucks required on day 6, okay, and 14 trucks on day 7, but only 10 is available. So what was the solution? Yes, we had to utilize floats, and if we go back we can see that A, B, C, F, G and I are critical. So we could only move, we chose last time to move D, okay, so we actually moved D all the way to the end, and that actually resolved this. So this 4 actually moved to the end, and that resolved the over allocation problem. Okay, so we had this come down to 10 and this went up to 6. Now the question is, so what we did was actually move D all the way and we moved it to 14. That's what we did last time. Okay, the question is this the only solution? First question, does D need to use all its float? So right now when I brought D here, I have made it actually critical. Okay, so does D need to use all its float? No. What are my options with just D?
From day 10.
Yeah, I can start it from day 10. Okay, so there are 2 possible solutions with just D. What if I started on day 9? Over allocation. 6, 4, 1, it would have gone to 11. Okay, so if I choose to move D, I have 2 options. Are there any other options?
C is critical.
Yeah, C is critical, so I can't move C. So I can move E and H. Can I move E?
Yeah, E and H are having shared floats.
Right, so if I am moving E, I first have to move H first. So you can see E is here, H is here. So there is possibly another solution moving E and H. We will explore this at a later stage. Okay, but realize that when we moved D last time, it was only one of the options, and we chose to move D all the way to the late start, but again that is only one option. Within D itself there are 2 options, but in addition to D there are other options of resolving over allocation. Now as a planning engineer or project manager, when you look at these options, you have to now, there are other constraints which will work into which option you choose. So for example, D might be being done by a subcontractor who is not easily available. So you will say that look, I fixed this person to start on the early start date, and there is no way I am going to change my schedule on him, whereas E and H are subcontract types of work in which more kinds of people are available to do, or the subcontractor is flexible on that. So there are many constraints that come into finally deciding which activity to move, but the important thing here is to realize there are multiple options. Okay. Now let us move to another problem. This time we are taking cash as a resource, and you can see the problem statement here. The network is a little different from what you have done earlier, but I would like you to start drawing this network. We will not solve the whole, I do not want you to solve the whole network in class, but I want you to get a feel of what the network is. So please start drawing the network, and you will find, I do not want you to solve the network as of now, I just want you to get a feel. So there are, if you look at, there is a path going A, B, C, D to J, then there is A, E, F, G, J, which is critical, then A, H, I, J, and then there is actually another path A, B, F, I, J, A, B, F. So there are a few more paths than our simple networks we have considered so far. Okay, so the project duration here is 19 months, and once we do this, if you go back, the problem statement says the total value of money for activity A is 45,000. This is spent over 2 months. Okay, so unlike where we said the daily requirement of a truck was 2 per day, here this is the total value of that activity. Okay, so if we want to find the monthly expenditure of cash, of the money that is going to go, what do we need to do? How do we need to apply the same principles of resource?
You assume a linear.
Yes, so that is the first task. We will assume that the total value is equally divided for the duration of the activity. That is, for our purposes in class today, we are going to assume it is equally divided. In reality, it is certainly not equally divided, and one of the challenges becomes actually finding what is how will you divide this over the time period which you are doing the work. Okay, so there will be different variations. Some of the simpler software only allow you to do equal proportioning of the resource or the cost or whatever it is. Most professional software will allow some function or some variation where you can talk about how you are going to actually how you are spending the money, how it varies, and there need not be a function. It can be totally based on factors which is totally discrete.
That will entirely depend on the activity.
It will depend on the activity, it will depend on other activities, it will depend on so many things. So some activities you might want to load it in the beginning and then ease off later, so it is discrete. I mean, you can have a function, but in general it is discrete. Okay, so here we have assumed equally, so we have taken just the total value here, okay, and then divided by the number of months to see monthly value. So this gives you the monthly value of the monthly expenditure on each of the activities. Is that okay? Now, so the first point we want to address is to find out a month. If I am going to be spending, if I am going to be doing this activity on this schedule, how much money will I be spending each month? Okay, so here we go. We have taken the schedule. This is the early start schedule. Okay, we have put this in the form of a bar chart. We have loaded the bar chart with the value. Okay, and all we do is in the first total here, what we have done is just added up, just as we did for the trucks. We have just added up, but this is money. Okay, and you find this is the bar chart you get for monthly outflow. Now you can see that the outflow here is in certain months has exceeded what has been allowed. So we can say that you're only going to get 100,000 rupees to spend a month. If you exceed that limit, I cannot allow you to do it. Might be there is some kind of a credit limit or something which is exceeded. Okay, so this is when we look at it from an early start perspective. Now when we go to a late start perspective, what we have done is moved all the activities with float. So you can see I have the area here, which is all the white area shows float. Okay, the grayed out area is where there is no float. So what we have done in the next step is moved everything to the late start. Okay, this is everything to the late, and this still does not resolve our problem. Okay, now the question is there a solution in between these two which will resolve the problem? And what we would like to discuss here is is there only one solution, multiple solutions? How would we go about finding the solution to this? So I think when we look at this representation, we should be able to find a solution, right? But one is, can we come up with certain set of rules, or can we what are the ways in which these solutions one should go about looking for the solutions? And now we will do it manually, but at a later stage if a computer is going to do it, how do we automate such a process? Those are some of the challenges actually in the resource allocation domain. But as of now, let us see how we can do this manually. What I have done is put this into a spreadsheet. Okay, you can see the early start, okay, the loaded bar chart, and the equivalent bar, the bar chart is below. So I put it in this form so that we can move things around. So as I decide to move this here, the bar will change. Okay, and you know the limit we have is 100,000. Okay, so let us so you can make suggestions and we can actually move the bars around. So even now we have exceeded 100,000. So so let's explore the possibilities with which we can work so that this is below 10,000. So now let's discuss how far can I move C? No, remember.
You can move it all the way, but it's still constrained with precedence.
Yeah, it is still constrained with the D. Yeah, it's exactly. Yeah, I can't move C beyond D. Okay, you have to go back to the network. I can't move B beyond C. If I move D, then I can move. Then it gives space to move C. So remember that you have a B, C, D. They are linked, and H and I are linked. Okay, so here you have B, C, D. So right now, yes, C can move, but it has to stop here because it can't move beyond that. Once C moves, B can move. Okay, so what would be the order of? So right now, if I look at what is being over allocated here, it is C that is loading it, right? And right now E, I can't move E at all. The other option I have is to move H. Okay, remember H can also move, and H has free float on its own. Okay, now how did H get free float on its own? Without, even though H and I are linked, how did H get free float on its own?
Because I is linked to F. Yeah.
Yes.
So
Yes. So F is a critical activity, and that precedes I. So I early start is controlled by F. So that is how H got free float. So I can move this now. Does it resolve my problem? Does it solve my problem? No. Okay, it's got a bit better. So now I can move this one more step. No. Okay. So it looks like here there is, so this is a bit of what we call a trial and error process. So this is now again exceeded. So what should I move it here? And move this out. Okay, so I have resolved this part. Now I can just move. Yeah, that doesn't matter in this particular case. Okay, so this, now is this the only solution?
You can shift H also.
You can shift H.
Yeah, I can. So if I can go back to my old let's just take back all the moves we made. Okay, and now I'm actually going to bring this back to the early start. I'm going to just simply move H more. Okay, now okay, that didn't solve my problem. So here I have, what can I do now?
We can shift I
Yes, move I out all the way to the end,
and D.
and then now move D in between.
Yeah, 13 and 14.
Okay, so yeah, I had moved by one more. Okay, so here is the second solution. Now, because this is a simple network and because we have only one resource here, we are able to shift these things around and find solutions. Okay, and obviously we are not adding context to the what activities are A, B, C. In the real world, when we have to, like we discussed earlier, we have to see what we can move and the cost of taking up float and things like that. Okay, but the ultimate goal would be to find some way of associating cost with these moves and find the least cost solution to resolving the over allocation problem. Okay. So so in this particular case, look at this slide, we resolve the over allocation by moving this to the so this is this was the solution we came up with, right? Yes. So this was the second solution which we came up with. Any questions?
You can formulate a linear programming problem.
Is it a linear program? Think about it. Are these, what is the dependency between the values? Is there any kind of dependency between the values? Assume that the cost is equally divided for each activity. That's fine. Other than that, what is the relationship between the activities? Precedence is a relationship. Other than after that, there's almost no relationship between, other than how each activity has its floats, each activity has its free float, and there is a dependence between the successor and its float. Other than that, the critical activities are, there is a very complex dependency. How is E dependent on, for example, C? What is the relationship between E and C? Okay, there is no specific relationship, but there is a relationship between E and I. Yes, there is a relationship, but when I come in here and look at E and look at I, in what way is that relationship modeled, or how will I model it in a linear programming? Okay, so the optimization, when you model it as an optimization issue, it is one of the toughest optimization models. No, but again, when we say trial and error, that means what would be the solution space for something like this? Okay, in this particular case it's reasonable, but as the number of activities grow and the number of steps you can move it grow, it will become very large.
But it is possible to program in Excel, right?
It is programmed, so this is something which you can try if you know Solver. Solver is not just linear programming, it goes into more advanced algorithms, but spaces like this are good for genetic algorithms, okay, and other techniques of optimization. Yeah, so how many variables are here? What are your decision variables? Cost is your cost is your objective. Minimizing I mean actually you're not changing, you want to make so you want monthly cost to be less than 10,000 as an objective. What are the decision variables?
Changing the duration of the total duration of the activity on the table.
Right now we are not changing duration.
Start and end date.
How much to shift an activity by?
How much is shift?
Okay, so if you look at the combination of shifting possible, how many combinations are there? There'll be, I mean we can start counting. Okay, so for each shift of this, so for example, for right now this can't move any, so I can move this by 1 2 3 4 5 6 7 8 9 10. Then for each of those shifts 10, I can move this independently, this independently. Okay, so that is the solution space we are talking about. It's going to be very large, and that is, so the ultimate the decision variable is how much should I move each activity by. Okay, and in some solution might be all 1 2 3, here we have 5 activities which could be moved. So my decision space is activity B, comma, number of steps, number of days by which I should move. Activity C, number of days. Activity D, number of days. That is my decision variable, and the number of days might be 0. Okay, so if we go into the solution we just got here, the solution says C by 1, D by 1 2 3 4 5 6 7, okay, and I by 2, and H by 1 2 3 4. So that would be the solution which gave a acceptable result. Okay, now a solution which says B by 0, C by 0, okay, would that give an acceptable result? I bring C back here. Yes, it would also give an acceptable result. C by 0 and D by the same amount, H by the same amount, I by the same amount would also give an acceptable result. Okay, so we have kind of, so that is the more advanced areas of looking at resources, optimizing resource allocation, and here again we are talking about here we are just talking about cache resource and a single resource and a single project. Now when you scale it to the multi-resource, multi-project kind of a problem, it becomes more complex. Okay, so when we actually put all of these the 3 charts, so we have the early start here in blue, in purple we have the late start, and then the balanced chart here. You can see how, again the emphasis is how float can be used to vary your resource profiles. Okay, so far we have actually talked about mainly looking at moving the whole activity. Okay, what are the other possible strategies? Yeah, so now right now we are moving the whole activity by 2 months, we are keeping the duration constant. Okay, so another another possible way, yeah, yes, I can increase the duration, in which case my cost per month, I am assuming my total cost will remain the same. Yeah, no, my total cost will remain the same. I am assuming my total cost will remain the same, but so my cash required each month will decrease. I am going to increase the duration. Yes.
Then the labors, but in realistic use the cost will increase.
The cost will increase, but my monthly cash flow will decrease. So my total cost might, I mean even if in the assumption which one could work with is saying cost won't increase, my monthly cash flow will decrease, and then I could bring it within the limit I want.
Even if the total project cost increases, that is not a constraint right now on us, because we haven't said that the total cost of the project should remain constant.
And a lot of times this happens.
If we increase a particular activity duration by a month and the cost increases slightly, it won't affect because we are able to optimize the cost for each.
And see, if you are going to increase the duration of a critical activity, certainly the project duration will increase. Right now you are going to increase the duration of a non-critical activity, project duration won't increase, but overall cost might increase, and right now we are not looking, I mean that is one possibility. The other possibility is that I increase the duration by just mobilizing less resources, and my monthly expense declines, and this is very commonly done on projects. Okay, they do not have the cash flow to sustain an intense activity, they will decrease the level of the activity, which might not be the most efficient way to finish the project, total cost might be more later. What about compressing? Instead of trying to do this in 2 days, I try to do the whole thing in 1 day, in 2 months I try to do the whole thing in 1 month. It will spike my cost, but if I have a slot I can fit it in, that will also help me to manage my overall monthly expenditure limit. If I have a 1 month where it is low and my float can overlap with that, then I will do that. Any other strategy you can think of? I could split. Okay, I can take, for example, something like C, and I can say I am not going to do it on 4 and in consecutive time, I am going to do one part of it here and then another part of it later. Does not apply in this case, but I could actually split an activity, meet expenses in different stages. Okay, again not necessarily the most efficient way to do it, but if my cash flow dictates that, that is what I need to do. Okay. So I mean we can kind of illustrate some of these things. I can take this, let me take this, I can just decide to take this and split it here, so this would be the split. Okay, and this can actually move all the way to here. Okay, so if I had a even, if I had a different benchmark, that is what I could do. Okay, so that would be the split.
So is there a way to rate the solution?
Yeah.
The feasible solution that you got?
Right. So now you need rules.
So that you can get to the better solution.
Right. So what? So there, for depending on project situations, yes, there are ways to rate solutions, and ultimately what you want to do is use minimum amount of one rule. One rule you can say is I want to use minimum amount of float. Okay. I want my solution to be in such a way that I do not go to the late extreme, but I use minimum amount of float of all my non-critical activities. Okay, that would be a simple way to rate. Okay, now what we have here is just the cumulative, the S curve. Okay, this is for the early start, this is for the late start, and this is for the balanced solution which we got, the S curve, and if we put all 3 curves together, this is what we get. Okay, so you get an envelope, you can, we said this is the early start curve, the late start, and in this particular case we have decided a cash flow which is in between, and all of the other flows, so long as we are within the floats, will be between these 2 extremes. Okay.